Okay, I've had a change of mind. I think I was wrong about the Christmas tree problem. That's Advent of Code, Day 14, Part 2. And I want to show why I was wrong and why I think the problem was a lot more fair than I gave it credit for. So let me look at my solution. Solve B. Okay, so we have a grid with a width of 101 and a height of 103. And since it wraps around, that means that at least, well, once every 101 steps, all of the robots are going to be aligned correctly in their x-coordinate. And once every 103 steps, all of the robots are going to be aligned correctly in their height component. So we just need to find when this happens for both of them at the same time. So let's just take a look at the output. So what I'm going to do is I'm just going to iterate one step at a time. Okay, and I need to resize things so that it looks correct. Okay, so what I'm doing, I'm just gonna step through, and I'm gonna look for when there is some alignment horizontally or vertically. Okay, so that's vertical alignment. We see a horizontal spread, but we see that there's some structure vertically. So that means that whatever the solution is, it's going to be 18 mod 103 because the height is 103 tall. So if we pull up a calculator over here. Well, I made that way too big, didn't I? Okay, and what we're going to do is we're going to use Chinese remainder theorem. So we have the height is mod 18 103. Okay, and then we're going to keep on stepping until we see structure in the width. Okay, and now we have structure horizontally, meaning that every robot has its correct x component, even though it has a effectively random y component. And so that means that the width is mod 77 101. And then if we just want to find when both of these are true at the same time, we can use Chinese remainder theorem. Chinese, and then height and width. And that's going to spit out the correct answer at 8258. So we can go back here and we can go 8258. And there's the Christmas tree. And so I think this is a totally fair problem, but it's fair in a slightly different way. Like I typically approach these problems thinking I need to write code to solve it, and I just am looking for an efficient algorithm. Whereas you do write code to solve this, but some of the algorithm is in just understanding what you would see every 101 steps, or what you would see every 103 steps. And if you want to replace the manual scrolling, if you want to replace this with code, then you can write pretty simple code to look for let's call it a non-uniform distribution horizontally or a non-uniform distribution vertically, looking for some structure. Because if you just measure just the x component of all of these robots, it's pretty uniform. Meaning, and so you would expect that structure that you're looking for is going to be, if it's going to make a picture, it's going to be somewhat non-uniform. And there's a lot of ways to do that. You could measure the standard deviation of the x component and the standard deviation of the y component, or you could measure them against a uniform distribution, or there's a lot of different ways that you could do it. You could simply look for regions that have a bigger cluster. They have let's call it an excess of robots. However you decide to detect it is up to you. Obviously, I'm just detecting it manually, visually. And you only really need to detect two things. You need to detect when it's a horizontal alignment, and you need to detect when it's a vertical alignment. And then you just need to do Chinese remainder theorem. And you can do Chinese remainder theorem in Python quite easily. You just need the extended Euclidean algorithm and then something called Bézou's identity. which comes out of the extended Euclidean algorithm, and you'll get these two numbers. So this number right here, this 10403, that's just 101 times 103. It's a useless number, but this is the unique solution mod this number that has both 18 mod 103 and 77 mod 101, and that's where the Christmas tree has to be. So I think it was a much fairer problem than I originally gave it credit for.